A comet near the sun just exploded in brightness, its tail now fanning wider than 5 full moons. Just days later, the sun unleashed its most powerful flare in months, blasting a wave of plasma straight toward that same comet. Now, that comet, R2 Swan, is heading toward Earth, fast. In a few short weeks, it will make its closest pass just as an interstellar object aligns with it in the sky. What happens when a cosmic visitor meets solar fire? Let's explore this together.
First light, the outburst begins.
Comets are notoriously unpredictable, but what happened on September 26th caught everyone by surprise. Just 2 weeks after its closest pass to the Sun at a perihelion of 0.5 astronomical units, Comet Swan suddenly roared to life. Initially, it was a faint object, but amateur astronomers in Japan and Australia noticed a dramatic surge in brightness overnight. This wasn't a minor flicker. The comet's brightness leaped by a full magnitude, from 7.4 to a peak of 5.7, pushing it into naked-eye visibility under dark skies. What caused this? As the comet swung away from the sun, intense solar heat penetrated its frozen nucleus. Pockets of sublimating cryovolatiles like frozen carbon monoxide and carbon dioxide buried for millennia reached their breaking point and exploded through the crust. This outburst ejected a massive cloud of gas and dust, dramatically expanding the comet's atmosphere, or coma, and feeding its enormous tail. According to cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory, such outbursts provide a rare glimpse into the primordial material from which our solar system was formed. This event signaled that Swan's inner engine was now exposed, making its next moves completely unpredictable, and turning it into a prime target for skywatchers worldwide. The sudden release of energy was so significant it altered the comet's light curve, deviating sharply from all predictive models.
Anatomy of a tail.
What does it really mean for a comet's tail to be wider than 5 full moons? Let's put that into perspective. We're not talking about a small, fuzzy patch in the sky. This is a massive structure, stretching over 2.5 degrees, which translates to a physical length of millions of kilometers. For observers, even in suburban areas, this makes it a stunning sight in binoculars. A comet actually has 2 distinct tails. The first is the dust tail, made of heavier particles pushed back by the pressure of sunlight itself, giving it a yellowish-white glow. This tail curves gracefully as it follows the comet's orbital path. The second, and often more dramatic, is the ion tail. This is composed of gases that have been ionized by the sun's ultraviolet radiation, creating charged particles like carbon monoxide ion CO+ that glow with a distinct electric blue light. Because these particles are electrically charged, the ion tail is sculpted by the solar wind and its magnetic field, always pointing directly away from the sun. With Swan's tail being so expansive, even small telescopes can reveal incredible details. Knots of dust, shifting streamers, and sudden kinks. Amateur astronomers are already capturing these changes, creating time lapses that show the tail evolving hour by hour. This massive, unfurling tail isn't just for show. It's a giant, sensitive windsock in space, about to get hit by a solar storm.
The sun awakens.
Just as the comet was putting on its show, the sun, which had been quiet for weeks, decided to join the party with its most powerful eruption in months. On September 28th, at 0843 Universal Time, satellites from the GOES network detected a massive spike in X-ray emissions, jumping from a background level of 10 to the -6th to 6.4 times 10 to the -5th watts per square meter. An M6.4 class solar flare had erupted from a magnetically complex sunspot group designated active region 4232, then rotating into view on the sun's southeastern limb. M-class flares are the second strongest category, and a 6.4 is a significant event powerful enough to cause radio blackouts on the sunlit side of Earth. Scientists at NOAA's Space Weather Prediction Center, like lead forecaster Dr. Alexei Pevtsov, immediately began analyzing data from the Solar Dynamics Observatory's AIA instrument at multiple wavelengths, including 131 angstroms, to assess the flare's power and more importantly, what it threw into space. The energy release was equivalent to millions of hydrogen bombs detonating simultaneously. The timing was incredible. Just 2 days after the comet's own eruption, the sun had fired a warning shot into the exact same quadrant of space.
Plasma on the move.
So, what is a coronal mass ejection? It's a massive eruption of plasma and magnetic fields from the sun's outer atmosphere, the corona, releasing billions of tons of material into space. Think of it as a solar cannonball. This particular CME shot out from the sun at a speed estimated between 800 and 1,000 kilometers per second. Forecasters at the NOAA Space Weather Prediction Center quickly began running its trajectory through their WSA-NLEL model, a sophisticated computer simulation that predicts how solar disturbances travel through the solar system. Using data from coronagraphs on satellites like the Solar and Heliospheric Observatory SOHO, which create an artificial eclipse to see the sun's faint corona, they determined the CME was not aimed at Earth. Instead, the model showed its path would sweep directly through the sector of space occupied by Comet Swan. The timing was remarkable, just 2 days after the comet's major outburst. This set up a rare opportunity for scientists to watch what happens when a powerful solar storm collides with a comet. The plasma density in the CME, while incredibly thin by earthly standards, is more than enough to overwhelm the comet's own magnetic field. The question for forecasters was no longer if the CME would hit, but when, and how dramatically it would affect the comet's enormous, newly expanded tail.
Magnetic scissors.
So, what happens when a comet's tail, which is a magnetic structure, meets a massive magnetic cloud from the sun? Sometimes things just snap. This phenomenon is called magnetic reconnection, and it's one of the most explosive processes in the solar system. A comet's ion tail is made of plasma, held together by magnetic field lines streaming away from the sun. A CME, however, is a tangled web of powerful magnetic fields, often containing a strong southward-pointing component, known as the Bez field. If this southward Bez field, with a strength potentially exceeding 20 nanoteslas, slams into the comet's oppositely directed magnetic field, they can't merge. Instead, they collide, break apart, and explosively reconnect into a new shape. As space plasma physicist, Dr. James Drake has explained, this process converts magnetic energy into kinetic energy with incredible efficiency. When this happens, the energy release can be immense, acting like a pair of magnetic scissors that cleanly severs the entire ion tail from the comet's head. This is called a disconnection event, and it can happen in a matter of minutes, leaving the old tail to drift away as a new one begins to form.
The forecaster's puzzle.
Predicting the outcome of this cosmic collision is a huge challenge. While models showed the CME heading toward Comet Swan, solar ejections don't travel in perfect straight lines. They expand and can be twisted by the ever-present solar wind. The best estimates from the SWPC place the CME's arrival at the comet between 48 and 72 hours after it left the sun. The key uncertainty was whether the most intense part of the CME, with a strong southward BZ component, would score a direct hit on the ion tail. Without a direct impact on Earth, scientists have limited in situ data. However, data from spacecraft like NASA's Stereo-A, which observes the sun from a different vantage point, helps create a three-dimensional picture of the CME, improving the forecast. Dr. Carl Badams of the U.S. Naval Research Laboratory, a leading expert on comets observed by SOHO, noted that these events are nowcast situations, where data is analyzed as it arrives with little room for error. Every major forecast center flagged the event for comet researchers worldwide. For Earth, the risk was zero. For Comet Swan, however, the incoming plasma was a loaded gun. The world's astronomers were now watching, waiting to see if the tail would simply ripple or completely break apart.
Citizen science mobilizes.
When a cosmic event like this unfolds, the big observatories aren't the only ones watching. A global network of backyard astronomers becomes the front line. Professional telescopes, well, they have schedules booked months in advance, so they can't always drop everything to watch a single event. But citizen scientists, however, they can provide continuous round-the-clock coverage. This is crucial, because a tail disconnection event can be incredibly fast. unfolding in less than 2 hours. An amateur astronomer with a modest setup, like a 10-inch reflector and a modern CCD camera, could actually be the first person to capture the collision. Organizations like the Association of Lunar and Planetary Observers, or ALPO, have entire sections dedicated to coordinating comet observations. Renowned astrophotographer Damian Peach has shown how high-resolution amateur images can rival those from professional instruments. These observers are not just taking pretty pictures, they're collecting valuable scientific data, or photometry, that can be used to measure brightness changes and map the tail's structure with incredible detail, helping to build a global record of this rare encounter.
The perfect alignment.
As if a dramatic outburst and a solar storm weren't enough, the cosmos has thrown in another twist. On October 21st, 2025, Comet Swan will make its closest approach to Earth, passing just 0.26 astronomical units, or about 39 million kilometers away. This close pass is remarkable for another reason: the timing. It occurs during a new moon, meaning the sky will be at its darkest, providing perfect viewing conditions. And there's more. On the very same day, an interstellar visitor designated 3I Atlas will be in the same general region of the sky from our perspective. While separated by millions of kilometers, this alignment offers a rare chance to compare a comet from our own solar system with an object like 2I Borisov, which had a distinctly different chemical composition. Such alignments are invaluable for testing our models of solar system formation and planetary science. The geometry of Swan's close approach also enables a cool trick for amateur astronomers: the parallax effect. Because the comet is relatively close, its apparent position against the background stars will shift measurably when viewed simultaneously from different locations on Earth, allowing backyard observers to triangulate its precise distance.
Southern skies, spotlight.
For these crucial weeks, the best seats for this cosmic show are in the southern hemisphere. From major observatories like the Siding Spring Observatory in Australia to backyard setups in South Africa and South America, Comet Swan will be high in the sky after sunset. Its path takes it through the southern constellations of Grus and Piscis Austrinus, passing near the bright guide star Fomalhaut. Viewers can use this star as a guidepost to locate the comet, which will appear as a fuzzy star with a long, faint streak extending from it. Even a standard pair of 7x50 binoculars will be enough to reveal the tail, stretching over 2.5 degrees, the width of 5 full moons. For those in the northern hemisphere, the view will improve throughout October as the comet climbs higher in the western sky after midnight. The checklist for observers is simple: find a dark sky, use a star chart to locate the comet, and watch for any changes. By taking images every few minutes, observers can create time lapses that will reveal the tail's motion and any sudden disruptions caused by the solar wind in stunning detail.
Cosmic forces collide.
Let's bottom line this. We have a documented encounter between a powerful solar storm and a comet that has recently undergone a massive outburst. Scientists are eagerly waiting to see the effects of the CME, reminiscent of the 2007 event, when NASA's Stereo spacecraft watched a CME completely rip the tail from Comet Encke. Dr. Geraint Jones of University College London, who studied that event, emphasizes that these collisions allow us to probe the comet's invisible magnetic environment. However, it's crucial to note that the exact outcome for Swan remains to be seen, and no direct link has been scientifically established between the M6.4 solar flare and Swan's earlier outburst. The timing is likely a spectacular cosmic coincidence. What is certain is that this October provides an unprecedented window for both professional and amateur observers to witness the dynamic interplay of cosmic forces in real time. Key questions remain. How much material will be stripped from the tail, and what can that tell us about the comet's composition and the sun's power? The journey of Comet R2 Swan is a rare and unfolding story, a live experiment in solar system physics happening right before our eyes. We are witnessing a truly unique cosmic alignment: a volatile comet, a powerful solar storm, and a front-row seat from Earth. What will happen when the CME slams into Swan's tail is still unknown, Will it be a gentle ripple, or a dramatic disconnection that severs the tale completely? The only way to find out is to look up. This is a rare opportunity for anyone with a pair of binoculars or a small telescope to contribute to a global science campaign. The universe is putting on a show, reminding us of the immense and unpredictable forces at play. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech.